Okay, again, thank you guys for your patience with me. Appreciate you being here, and yeah, I've had a few technical difficulties getting started, but I'm here and ready to go now. We're going to do some practice problems to kind of review for the exam, and the exam's on Wednesday. And then my goal is tonight to read your rough drafts. For those of you who've submitted rough drafts of your paper, I'm going to try to read those tonight and get those back to you. So that's my plan. So for the exam, just to remind you guys, I'm going to allow you to use a calculator. And also, if you look in your book in Table 1, I'm going to make a Xerox of that and give to everybody. So that is the table of all of the it's the least primitive roots for each prime number from 2 to 1,000. So if you're trying to find a primitive root of a prime, you can't find all of them in this table, but you can find one at least. And of course, once you have one, we'll review this today, you can then find them all. Okay, so anyway, those are the things I'm going to give you for the exam. As I've already explained to you, I'm going to allow you to take one part of one problem home. Okay, you can decide during the exam, and you'll just write take home on whichever part it is. And then after the exam, I'm going to post a blank copy of the exam. You'll go to that, print out the page that you're going to, that has the part on it that you're going to do, and then you'll turn that in by Friday. So that's how it'll work. And then in addition to that, you've got the 2 proofs that you're learning. So there's quite a bit of points you can get, without too much stress if you plan things well. So that would be my advice. So the review packet has everything that's going to be covered, the sections that are going to be on it, all that kind of good stuff. Kind of starts with the Euler phi function, calculating phi of n, something you're going to want to be able to do. And then works its way into things like the order of an integer, modulo n, and then primitive roots, of course, indices, and then we did a little bit on cryptography, some basic cryptography, obviously. About that much I could do with that, but I could ask you to do some kind of a computational thing with cryptography, I believe. And then there was the stuff on quadratic reciprocity, solving quadratic congruences, and some of those results on the Lagrange symbol that we covered. So those are really the main things. Tomorrow in class, I'm going to be starting chapter 11, so we're going to go into something totally different that won't be on the exam. So that's kind of my game plan. The 5 theorems that I'm going to be choosing 4 of are on the review packet as well, so hopefully you've started learning those a little bit. If you have any questions as you're preparing those, anything from your notes that doesn't make sense or doesn't look right, feel free to ask me. I do tend to grade those proof problems a little more strictly, just because they are kind of very prescribed out in advance and everything. And then some additional, just a list of all the important theorems, properties about phi of n, properties about primitive roots, properties about the Lagrange symbol, all those kind of things. And then just some things to be able to do that we have kind of talked about. And then there's some sample problems in here too. So there's actually quite a bit that you can look at. There's also a sample exam that I posted online. So I'd suggest that you try that out as well when you get a chance. Okay? Does anybody have any questions on the overview, really? If not, my main thing I want to do today is just throw some problems at you. When you're in a particular section, doing a particular problem from a particular section, you're a little bit biased already because you know kind of what the topic is. So one of the things I want to do here is really mix it up. I want you to practice seeing the problems in a random, sort of being thrown at you in kind of a random order. Okay, so that's what we're going to do. Okay, all right. So if there's no questions, then I'm going to go ahead and get started. Okay. So these are not going to be, and I also have these notes from this review session, and I Xeroxed them, so they're up on the website as well. I'm not going to go in order though of this packet, so just keep that in mind as you're taking notes today. Okay. So let's start off with number 1, practice problem number 1 right here. I'm going to try to get a better marker. What I want you guys to tell me is how many primitive roots each of the following numbers has. Okay? So how many primitive roots are there for, and we're going to do a few of these. Okay, the first one is going to be 106. Actually, I'm going to write them all down, and then you guys can think about them for a minute. So 106, the second one is going to be 375, and then the third one is going to be 343. Okay? So given any positive integer, I could ask you how many primitive roots does a particular number have? So for 106, what would you recommend that I do first? Break it up into primes. Okay, good. So it breaks into what? 2 times 53. Okay, and so then what's the formula for the number of primitive roots? Phi of n. That's right. So does this have a primitive root, by the way? Does 106 have a primitive root? Yes. Yeah. So do you remember which numbers have primitive roots? Okay. So let's just review that theorem right now. I think it's theorem 8.10. I just want to get this reviewed right away. So n has a primitive root. If and only if. Can somebody remind me, what are the possibilities? 2, 4, p to the k, and 2 times p to the k, and here p is odd, right? P is odd, and k is at least 1. Okay, so does 106 have the right form to have a primitive root? Yeah, it's of the form 2 times a prime, right? Okay, so then we need to calculate phi of 106, right? What is phi of 106? So just let me remind everybody that phi respects multiplication. So in other words, if you have two numbers that are relatively prime, so 106 is 2 times 53, phi of 106 is going to be phi of 2 times phi of 53, okay? So I can calculate that. That's going to be phi of, now phi of any prime is just prime minus 1. So phi of 2 is going to be 1, and phi of 53 is going to be 52. Okay? Now I have to figure out what phi of 52 is. Yeah, so you need to actually factor 52 now, right? So this is phi of 4 times phi of 13. What is phi of 4? 2. And phi of 13? 12. And so the answer is 24. So there are 24 primitive roots of the number 106. Okay? Does that make sense? So there are 52 numbers that are relatively prime to 106. Out of those 52 numbers, there are 24 of them whose powers will generate all of those 52 relatively prime numbers. If you just take r, r squared, r cubed, and so on. Okay, does that make sense? So we have 24 primitive roots out of the 52 elements in mod 106 that are relatively prime to 106. Okay. All right, let's do the next one. 375. What's the factorization of 375?
Well, 15 times 25.
Let's get it down to the prime factors. And actually, hold on. I corrected me on the last one. Let's get different people involved here.
5 cubed times 3.
It's 5 cubed times 3, right? 125 times 3. Okay. So what is the number of primitive roots of 375? It's 0, right? You know what I see for a popular wrong answer? People just do phi of 375. They forget that they first have to know that there is a primitive root. So if I give you a number that has no primitive roots by that theorem that I just erased, theorem 8.10, then you should just say 0 right away. Okay? All right, let's go on to the next one. 343. Does anybody know how to factor that? Okay, that's 7 cubed. Does that have any primitive roots?
Yeah.
It will, according to our theorem, any power of a prime will have primitive roots, and so we need to calculate phi of 7 cubed. Okay? So let's see. Does anybody remember the formula for phi of p to a power k? It's actually p to the k minus p to the k minus 1. In other words, you take all of the numbers from 1 through n and subtract off the powers that are, well, you subtract off the multiples of 7, and there will be 7 squared of those in this case. In general, p to the k minus 1 of those. Okay, so this becomes 343 minus 49. So that becomes phi of what, 294? All right, now we have to figure this number out. Oh boy, let's factor 294. Well, it's divisible by 2, and it's 2 times 147, times 147, I believe.
147 is 3 times 49.
And 147 is 3 times 49, so it's 2 times 3 times 7 squared, exactly. Okay? So we just do that factorization. Then we just use the fact that phi is multiplicative. By the way, that theorem is 7.2. That is one of the theorems that's in your list. It's a pretty long theorem that we proved shortly after the first exam. So we're going to do phi of 2 times phi of 3 times phi of 7 squared. And phi of 2 is just 1. Phi of 3 is 2. And phi of 7 squared would be 49 minus 7, which is 42. So the final answer here is 84. 84. Okay? Does this make sense so far? Yes, Shannon?
On an exam, would that be adequate amount of work, or would you like us to cite the theorem or anything?
I don't need to know the theorem numbers at all. I mean, it would. I actually think that this is probably just fine.
Or so
Yeah.
you want to state like
No, I may ask you to state some theorems on the exam, in which case then that's what you would be doing. But I don't think, in this case, it's pretty clear what you're using. So I think I'm okay just with that amount of work. Okay. Okay, let's go on. Let's go to another problem. I just wanted to. The nice thing about this one is it forces you to remember the theorem 8.10, which numbers have primitive roots, and then you have to know the properties of the Euler-B function, and you have to know that phi of n theorem. So there's a lot of things that go into a problem like that, but it's really not that hard. Okay, let's do another very computational type of question here. Part A, let's compute the Legendre symbol of 14 in mod 137. So this is more recent material. Okay. So, do you remember your properties of the Legendre symbol? That's what you want to use here. Okay. So the properties that we have, of course we have the quadratic reciprocity law. That's the one where you can flip a Legendre symbol over, but only if you have two distinct odd primes. So right now 14 is not prime, so I can't use the quadratic reciprocity law as it's stated now. I also have a multiplicative property. I can take what's on top and factor it and split apart the Legendre symbol accordingly. Anything that's a perfect square on the top can always just be discarded from that numerator if I want to call it that. And let's see, what other kind of things do we know? We know that this Legendre symbol is, so if I have like A with respect to P, it's congruent to A to the P minus 1 over 2 mod P. So you can always like brute force this thing, but that requires, if the modulus on the bottom is big, you're going to be looking at a really big power of A right here, so that's not necessarily what you want to be doing. Okay, so does anybody have a suggestion what we might want to do with this one to start off with? Okay, we can break this one up, right? We take the 14 and we can split it as, how do we split that one? 2 with respect to 137 and 7 with respect to 137, okay? Now remember that the quadratic reciprocity law does not work with the number 2. You cannot flip that one over. But you might be tempted to do it with the second part. This is now two distinct odd primes. Remember that if you want to flip a Legendre symbol over, you should probably be doing it in such a way that the smaller number goes on the bottom. That's what you want. And then also, you have to change the sign of the expression whenever both of the numbers are congruent to 1 mod 4. So every odd number is going to be congruent to either 1 or 3 mod 4. What about this one? Are both of these numbers congruent to 3 mod 4, or is one of them congruent to 1 mod 4? The one on the bottom is congruent to 1 mod 4. So I can actually flip this one over with no change in sign, right? So this is just going to stay the Legendre symbol of 2 with respect to 137, and I'm just going to flip the other one over completely, okay? Now the 137 with respect to 7, what can I do with that? Right, I can reduce the 137 mod 7. So you divide by 7 and keep the remainder, right? So I believe the remainder is 4. So this becomes the Legendre symbol of 2 relative to 137 times the Legendre symbol of 4 relative to 137. Okay? What can I do with the second part? It's just 1 automatically because it's a perfect 4 is a perfect square, right? So I'm down to looking at the Legendre symbol of 2 with respect to 137. Do you remember how to decide whether this is a +1 or a -1?
Yep. 1 or 7 mod 8, it's +1. 3 or 5 mod 8, it's -1.
Perfect. That's exactly right. So just remember the theorem from last week that we have a formula for the Legendre symbol of 2 with respect to p, right? It equals 1 or -1. It equals 1 if p is congruent to 1 or 7 mod 8. Oh, I'm not going off the screen here. And it's -1 if p is congruent to 3 or 5 mod 8. So we just need to figure out modulo 8, 137. Is that okay?
You're off just a little bit, but you know, maybe if I just
turn this thing a little bit, yeah, because I kind of zoomed it in.
Let's see.
It's a really wobbly tripod. We're trying here, guys.
Yeah, if you don't write past that,
We'll put all the
it should be
answers to
okay.
the exam on the other board for that. Okay, thanks. I won't go any further.
That's
Yeah.
perfect.
Okay, perfect. So 137 mod 8, is it, during that fiasco, did anybody figure it out? Is it 1? It's congruent to 1 mod 8. Okay, so that means that this Legendre symbol is 1. Okay, so the answer would be 1. So what does that actually mean? Let's come back over here and ask a second question now. And again, this is a great problem because it forces you to do several things. You can't flip everything over, so you can't just use the quadratic reciprocity law for everything. You do need to know some of these theorems. The other one that is the sort of the partner with this one is the one for -1, right? This one is a little simpler. It's equal to 1 if p is congruent to 1 mod 4, and 3 if p is congruent to, -1 if p is congruent to 3 mod 4. So that's a little bit easier one to remember. So those are two you just want to know cold. You just want to know those values cold. Okay, so let's just recall real quick that what it means that we get a Legendre symbol of +1 is that 14 has a square root in mod 107 or 137. So that could be a follow-up question here. So the follow-up question would go something like this. Solve for x, and the problem would be x squared congruent to 14 mod 137. So this is something that now we know there is a solution, right? How many solutions? There's at most 2. By Lagrange's theorem. So theorem 8.5 says that if you have a prime modulus, right, then if you create a polynomial equation, which is essentially what we have here, the number of solutions of that polynomial equation are at most the degree of the polynomial. So at most 2 in this case. Of course, once we find one solution, we'll be able to get another solution by just taking the negative of that solution, because you're squaring that expression, so when you square a negative, it goes away. As long as the negative of the number is not the same as the number, then you'll have your two solutions that way. And chances are, actually it's probably impossible for that number to be the same as its negative, because x is not going to be 0, obviously. So, okay, so anyway, this is the question. So does anybody have an idea how you could then actually come up with the solution here for x, or find a solution for x? Yeah, Jose?
Would it be possible to subtract the 14 to the left side, and then I remember there's this equation you taught us that we let y equal 2ax minus b. And then
Oh, that's a very important thing to know about. If I have a congruence ax squared plus bx plus c congruent to 0 mod p, right, and I ask you to solve that, then the way you're going to do that, and you're going to find one of these actually on the sample test, the way you're going to do that is to change variables in such a way that you make a new problem, which is y squared congruent to d modulo p, and the formulas for the y and the d. So the d is just your b squared minus 4ac discriminant that you're used to, and then the y is 2ax plus b, I believe, if I remember correctly. So you can actually make that change of variables. But that's if you have something like this, you're trying to change it into this. Okay. So here I don't have that. One thing you could do, I'm going to throw out a couple ideas. One thing you could do is you could say, well, I don't really know what to do with 14, but of course I can add 137 to it, and it's still the same number. If I happen to add 137 to 137 to 14, maybe I'll get a nicer number whose square root I just automatically know. Now in this case that doesn't happen because you get 151, which is not a nice perfect square. But you could add 137 twice if you wanted to. You could spend a lot of time. The thing is, you got to be careful on this exam. There is a time element here. Right? You can play around with this and say, well, I'm going to add 137 to 14. I'm going to do it and do it and do it and do it. And by goodness, I'm going to figure it out. Right? But you could spend the whole exam until you've come up with the right number. So does anybody have a little bit more of a, I guess, a foolproof or another idea how we can come up with a solution?
Take this problem home.
Take this problem home. Hey, there's a great idea. Take the problem home and then get your calculator out. Put it on a computer, So.
Do 14 to the p minus 1 over 2 congruent to 1.
Okay, so this is the element A essentially. So that would be a to the p minus 1 over 2. This would be, well, 136 over 2 is. Did you happen to find it?
I did it for like 5 minutes.
Say it again? That's what I was looking for. Let's use indices here to do this problem. Okay, in other words, if to use indices, you have to find a primitive root first.
And you have to make a table of it.
Oh, you don't have to make a whole table. You don't necessarily have to make the whole table. So for one thing, so 137, I bet it's in the book. Let's look, it's a prime. So in our table that we will have on this exam, we can go in here and we can find 137. 3 is a primitive root of 137. So from the book, r equals 3 is a primitive root. Okay, so let's try and take advantage of that. All right. So we have a primitive root, and maybe that'll help shed some light on this. So I can take the index of the whole equation. Do you remember how to do this? Okay, so we're going to review this from chapter 8. So take the index on the left side, take the index on the right side, and the mod changes to phi of 137, phi of n in general, and that's 136 in this case, right? So take index on both sides. Okay, so on the left side, I'll have the index I'll say base 3 of x squared, congruent to, on the right side, the index base 3 of 14, and then we're going to do mod 137 here, okay? So we do that. I can pull the 2 down. That's one of our, it works just like a logarithm, so many of the properties of indices work just like the properties of logarithms. I would recommend maybe reviewing the proofs of those properties of indices that we did in class, just to kind of refresh how those work. They're not that difficult. But one of the properties is indeed that you can pull down in front the exponent here. So we're going to get 2 times the index of x congruent to the index of 3. Oh, I wrote 137 here. I meant to write 136. Phi of 137, that's 136. Okay, and then the index base 3 of 14. So, let's see. So we need to figure out what the index of 14 is in this, using this primitive root of 3. Anybody have any thoughts on how to do that?
3 to the power is 14.
Right, 3 to what power is 14? Okay, so let's see if we can just try a few values and see if we can get anywhere with it. I don't know if that would help us. Let me come over here and give myself a little bit more room. Maybe too big of a number. You know I don't want the numbers to be too small. I want you guys to be thinking a little bit. I don't want things to be too easy to just kind of crack with too simple of a calculator. So, yeah, so if you calculate, powers of 3, and you're looking to see if you get 14, right? That's going to be the idea. Let's see.
What's the order of 14? Because then we could use that weird thing, maybe, like a to the h is equal to k over g.
Yeah, so we know that, the order of, so you're thinking of this theorem, this is a very important theorem, the order of a to the h, say mod n, right, is just the order of a in mod n divided by the GCD of h with the order in mod n of a. So, that's a theorem that you could use. So our modulus here would be 136. And so if we knew what the order of 14 was, would that help us? Yeah. Yeah, I don't know for sure that this is the right, I wanted to write it down just because this is an important theorem to know, but I'm not sure that that is really getting to the heart of what we need here. Let's calculate some powers of 3, just see what happens, okay? So 3 to the first is 3, 3 squared is 9, 3 cubed is 27. As long as I'm under 136, I don't need to reduce anything. 3 to the fourth is 81. 3 to the fifth is, well, it's 243. Yes. Okay, so, but we're,
Mod 137, right?
yeah, that's right, mod 137. So this is mod 137, it's what again?
106.
106. Okay, so let me just start putting the mod here. Mod 137, just so we get that down.
And multiplied by 3, 318, reduced to 44.
44, 3 to the 6th is 44. Okay, always mod 137 here. Oh,
Next one's 130.
I was looking at my notes here for the review session. You know what I wrote here? I said, now we need to solve for the index base 3 of x. Note that we would have to be given a table on the exam in order to solve this problem. Okay, so I could give you a table that would basically have this information in it, right? It would be an enormous table because there'd be 136 columns in it.
Yeah.
So that, I think that's the thing. This is I was thinking to myself, did I actually do this? So what were you going to say?
I was wondering if, because I'm sure we're expected to build the index table ourselves at some point.
You may have to. In fact,